Hello, this is Dr. Kozhanov, and this is lecture 6 of the online portion of Physics 4270, Introduction to Magnetism and Magnetic Materials that I teach at Georgia State University. So in this case, in this lecture is dedicated to magnetization dynamics. So before we begin, I would like to just overview what we were studying before. So first of all, if this is a magnetic material magnetized at a certain angle, we don't care about the angle. The way how we were treating magnetization of this material so far is that we were applying magnetic field at some direction, arbitrary direction, arbitrary magnetization, and there might be domains in this structure, or there might be no domains. We don't care. We are looking at the material from the outside. So what we do is we are measuring hysteresis curve, H versus M. And hysteresis curve, let's say if this is a ferromagnet, it might look something like that. This is a hysteresis curve. And if you're sitting here, if you set this field, H, let's say 1, then at that field, let's say this is saturated magnet. What it means is that at that field, this material would be completely saturated along the field. Let me remove this magnetization. Then if we sit somewhere here at this point, it is likely that at this point, let me use a different color. It is likely, you see the magnetization at this point is not saturated. At the same time, it is not zero. So what it means, it is likely that most of the magnetic moments are pointing in this direction, but there are some that have the component pointing against the field or at some angle, or it might be that the magnetization is just reduced by forming domains that are not necessarily opposing the field direction. So now what I imply, the main point, it doesn't matter what direction of these magnets are, is that even if there are domains, then if you set this field at this point, H2, then there will be magnetization domains there, and we can stay at this field, and it is likely that domain walls, as you remember, there is this area between the two magnetization directions called domain wall. It has certain thickness, domain wall. So what happens is that if you have a certain magnetization at certain magnetization direction, then when you set the field and you wait long enough, the domain wall will find its stable state. It will get pinned by impurities, and at that particular field values, it might even not move, or it might be first moving fast and then slowly. More than that, if you look at the time, let's say you look at the time of how magnetization reacts, H. Let's say that initially you sit somewhere here at the saturated level, MS, and not H. This is not H, this is time. I apologize, time. So initially you sit somewhere here, or you can sit, let's say, zero field. So here your field is 0, H is 0. Let me choose different color. And then suddenly you turn on the field equal to this negative field. Then you suddenly turn H equal H2 at this particular moment of time, right here. So what happens is then suddenly you apply negative field or field in the direction that is opposing the magnetization, and domains start to form. They start to form because the whole object it's not favorable for it to inverse magnetization. So we form domains. And what it means for the magnetization is that you form domains. The magnetization starts to drop and then starts to leveling out. So the mathematics of this job is fairly complex, and we don't have enough time for this, but this is what's happening. Initially, you have fast rotation and formation of domains, and then they still move. The domain wall is still moving. Let's say if you apply field in this direction, H, for this particular example, then this domain wall will be moving in that, now the domain wall will be, let me erase it. So I will erase all this. The domain wall will move to expand this domain. So the domain wall will move in this direction. But when you apply field, initially domain forms fairly quickly, and then the domain wall moves and it gets pinned by impurities or by the lattice disorders. And at some point, the fast motion stops and you get this slow motion of domain wall. So within a time scale, let's say if this can happen within microseconds or milliseconds, then this can be happening for hours, days, months, and years. So this small domain wall motion. And this process here, is probably defined by thermal fluctuations, because when you have domain wall pinned on the impurity, then it takes certain energy to unpin it. And if the pinning requires fairly large energy to get unpinned, to get moving forward, then what you need is a random fluctuation, thermal fluctuation that is big enough to unpin it. Therefore, and they are happening fairly rarely, and therefore this process is very slow. So what we can say is that within this time scale, from here and forward, the magnetization does not change much. And we can say that we are in sort of a quasi-stable state. We are in the stable state where the domain wall is moving very, very slowly, almost not moving within the time of our observation. So we are in the statics. And that's why we can measure this point here. And it means that as we sit on this point, if we set this field suddenly, we will jump to this field. The magnetization won't be fast enough to react to the field, but it will fairly fast go down and stabilize around here, and then it will likely to be moving forward unless the domain will find a stable pattern, or it will find a stable position and won't move at all. But this point is very stable, which means that if you measure it again, it will be exact the same point in the hysteresis curve, and therefore the hysteresis curve itself is reproducible. So this all stuff is statics. So we are in static state. We can stay there and magnetization will be stable. There will be no motion of the main walls. There will be no magnetization changes, and our material will possess the stable magnetic state. Now, if we this stable magnetic state allows us also to measure susceptibility. As you remember, susceptibility is the ratio of M to H, and basically if we take the ratio from this graph of each value, we'll get our susceptibility, and that allows us to say that, okay, your susceptibility versus applied field, if it is negative, or actually not susceptibility, but you can plot susceptibility as well. Let's talk about magnetization. And susceptibility would be sort of a slope if it's a straight one. So it's if negative, it's diamagnet. If it's small positive, it's paramagnet, or it can be super paramagnet, or it can be ferromagnet, or it can be antiferromagnet, and whatever. So all these things that we talked about, and you can talk about permeability or susceptibility, all these things imply that we set magnetic field, wait long enough for magnetization to turn, and measure its value. So what it means is that we know internal fields. So we can say that, for example, if you have a nanoparticle, it might have easy access, which means that you um, if, for example, magnetization points in this direction, we give it enough time for it to find a stable orientation, and it's likely to be aligned along the easy axis. Uh, so overall, we wait long enough time for magnetization to find its preferable energetic state. This is called a ground state. Ground state. So ground state implies that if you take, for example, a magnet with a random cube with a random alignment of atomic magnetic moments, then if you wait long enough, what would happen is that it would find its magnetization and it would find its preferable um, magnetization alignment, and that would mean that this is a ground state, which means that if you wait long enough, this magnetization ground state will not change with time. Okay, so this is what we were doing so far, and we discussed domains, different types of material, how they react to magnetic field, and we were discussing where these magnetic moments coming from and how they interact with each other. And so there might be anisotropy, there might be domain walls, and how this magnetization behaves in small magnets. It all implies that we set the magnetic field, wait long enough, and see the result. Now, this part of material that we are going to discuss in this lecture is dynamics. So, dynamics. So, what we are looking at is that if you take a particular magnetic moment, and apply magnetic field H, as you remember, what happens is that magnetic moment, there are different scenarios, but magnetic moment, or let me actually write B. It will start to precess, or it might relax, or it will turn towards the field. It depends on the particular case. But what we will be studying now is actually we will be studying the motion of this magnetic moment in presence of magnetic field. So we will be looking not at the end result, but rather we will be looking at how these small magnetic moments of individual atoms or domains or areas or maybe magnetization of the whole material or magnetic moment of a chunk, how they depend on time. And why they would be dependent, why there would be dependent on time? Well, even if you don't have any magnetic field, so if you don't have magnetic field and you have magnetic moment pointing in a certain direction, it would be pointing in that direction. There would be no change in the magnetic moment. But to induce that, what we need to do is we need to apply time-dependent fields. And time-dependent field might mean that, so for example, if I plot H as a function of time, it might mean that, for example, there was no field and suddenly we apply the field like a step function, or we can pulse a field. Let me use different color. We can apply a field pulse, so there is no field and then suddenly we apply the field and we remove the field. Or what we can do is we actually can get the field without having the period before. So we can have an oscillating magnetic field. And also you may notice that this field is a vector, which implies that we can, if you have magnetic moment, you can apply this time-dependent field to in different directions. So that was like a 14-minute introduction into what we're going to talk about. Now the next some amount of time, I don't know how much, but the next time I'm going to spend in reviewing what you already heard that I actually discussed in the lectures in class before going online. So magically, I'm showing you something that's already written, and that is something that you already seen before. So I'm not going to write this again. I'm going to use highlighter. And this is actually uploaded on iCollege. It's called Lecture 7, Quantum Origins of Magnetism. But the actual notes start not with a quantum origin, but they start with something that you have seen before. So now this is a PDF file, and you can find it there. It's saved. Oops, no. I'm going to annotate it. Yes. So if you remember, we discussed the spinning top. And this is not magnetism, this is mechanics, and you have spinning top in presence of gravity. So here is spinning top, it's positioned at certain angle, and gravity force points down. So gravity is equal to mg. It applies torque, tau, equal r cross mg. R is the distance from this pivot point to the point where the force is applied, and also we can relate it to angular momentum. So angular momentum is related to angular frequency, and I will go pretty fast through this. We already discussed this in detail, and these notes are also uploaded on iCollege, so you can look through this. Then we decided to relate. So the torque applied to that angular momentum is related to moment of inertia. Now we decided to see what's happening, so how things are changing in time. So this is the angle. So what happens is that position of angular momentum changes with time on angle phi here, and angular momentum changes obviously, and this is the simple geometry that allows us to write that the delta phi would be equal to delta L over L sine theta. So this is just geometric relationship between the delta phi, delta L, L sine theta. Following this, looking at this triangle. Now we divide it by delta t and take the limit in case of delta t approaching 0. And what that gives us is the following. It gives us delta phi over delta t. And d phi dt is actually our angular frequency. In polar coordinates, it's angular frequency. P stands for precession. That is a precession frequency. And then we take derivative of the right side. So this is a derivative dl dt, L sine theta. Now you may notice L itself is a constant, but delta L is what is time dependent. So L is this length of the angular momentum, but delta L is what describes its change. So therefore we take derivative only the L, dl dt, 1 over L sine theta. Now dl dt is torque. It is torque, and that is basically one of this Newton's second law for angular motion. And L itself is r cross mg, and if you write it in look not at the vectors but look at the magnitudes, rmg cosine theta, we can substitute it, and what we'll get is this. The frequency would be equal to this expression, or following that, this expression by substituting L value. And then there are different cases, R and L. So in our geometry, R can be collinear with L or anticollinear with L. So it depends on which way our top is spinning. And if we look at this relationship, R cross mg is equal to dl dt, we can rewrite this dl dt is equal mr over L. This is a sign of this dot product. So sign would be different dependent on the direction of orientation. L cross G. Okay, so and that can be rewritten again in this form. dl dt is equal to omega cross L. I will highlight it here. So this is a differential equation. A differential equation describing, as you see, it's written here, motion of spinning top in presence of gravity. So when you solve it, you would get an answer for L. L as a function of time. So as a result, L as a function of time. I'm sorry, this is PDF, very inconvenient to annotate. I'll get back to my notepad. So, that was an analogy. Now the next part in that lecture, and again, this is a reminder. You can actually scroll this video if you remember all this. The next part is the analogy. The important part is to remember this, because this equation is something that it has the form very, very similar to the motion of magnetic moment in presence of magnetic field. So what we did, next part is current loop, and as you remember, current loop is related to magnetic moment. So you can say that the current loop moves in magnetic field, but also you can treat it as a magnetic moment motion in the magnetic field. So torque applied to the magnetic moment is M cross B, M cross B, and angular momentum can be related. Angular momentum of the loop can be related to magnetic moment through the geomagnetic ratio, and we already talked about that a lot. Geomagnetic ratio. For a negative charge, there are different things about having M collinear or opposing L. But for electrons, if you have electrons moving there, then M has the opposite direction as L. Okay, and that if we substitute this M here and relate torque to angular momentum, then we will get this equation here. dl dt is L cross B. L is angular momentum, B is magnetic field, gamma geomagnetic ratio, and what we have is we have a relationship of this. And of course, if you scroll back, you can notice this. So M is related to L. You can substitute M there and you will get the same equation for M. Let me see, I think I should have it. These are references. Exactly the same as we are following the same procedure as we did for spinning top in presence of gravity. So d phi dt is equal to 1 over L sine theta dl dt, which is our precession frequency. Now this term dl dt, as we found previously, right, 2 pages ago, you can scroll video back, is equal to gamma L cross B. This gamma L cross B can be substituted here, and you will find the precession frequency. And precession frequency then is gamma B, and that's absolute value. This is Larmor precession. So what that is that if you have magnetic moment in presence of external magnetic field, it will precess around magnetic field. Now, this is the equation describing the precession, and precession frequency is equal to minus gamma B. So this is a reminder of what we already learned previously. Now, what I can do is I can take this equation here, dl dt omega cross L, and rewrite it in a different form. So I'm going back to my notes, and magically it should happen now. Okay, we are back on our notes. So let me do the following. Let me write down the main result of what we had before. So the main result is that if you have a magnetic moment M in presence of external magnetic field B, and it's not in the material, it's in vacuum, so we can write that B is mu naught H. Then for that, dl dt is equal to omega, oops, quite an ugly omega, cross L, omega cross L. where omega is precession frequency. So basically, our magnetic moment precesses around this magnetic field with a omega. Omega itself, vector, is equal to minus gamma b. Now, we did it for L because we implied that there is a current loop that produces. So there is this current loop with a current producing this magnetic moment. Now, as you remember, if you talk about atoms, then we would not be talking about L because there is L, angular orbital, angular momentum, but also there is S. And there are certain ways how they are being added, and they add to form J, total angular momentum. And J defines magnetic moment. We already discussed that. There is a way how we can calculate M. So basically what we can do is we can calculate that. We can convert this equation, we can replace L with J. And besides that, it's not convenient to work with omega. So I will rewrite the same equation that describes how magnetic moment moves in presence of magnetic field in this way. So total angular momentum in presence of magnetic field. So instead of L, we write dj dt. Now, instead of, let me keep it here so you would see. So instead of omega, we substitute it with this. And also we utilize mu naught h to substitute b. So I want to write everything in h terms. So therefore we have mu naught. Let me put gamma on front here. And I will change these two together to get rid of this minus sign. So that would be J cross H. Okay, so this is how we write. Now we can describe. So this is a differential equation. If you solve this, if you know H, then by solving this equation, you'll get your J as a function of time. Because here is time derivative, it's time dependent. Differential equation that gives you time dependence. What it means is that overall, you will know where your vector J points as a function of time. And you can see that a solution of this equation is a precession. This is a single J, so single atom possessing J in magnetic field produced by, well, we are in vacuum. Now, if we go back to our atoms, so this is my sketch of atomic lattice. So let me try to get the paper with a grid. Okay, here is grid paper. I hope you will see it. Sometimes it's not shown. Let me redraw my atoms to be more accurate. So, for example, these are atoms on a rectangular grid, two-dimensional view. So each of those atoms possesses total angular momentum J and basically magnetic moment. So for example, this one. Let me actually use red for that one. So here is your M or J, does matter. They're directly related. So what it means is the following. You have magnetic moment M or J, let's say J, this one, in presence of field H. This H can be produced, it can be external magnetic field. But at the same time, you should remember that there are other magnetic moments here, there, let's say it's a ferromagnet, it might be pointing in the same direction. So what it means, and we already actually discussed that, I remember. So what it means that every single magnetic moment of this crystal lattice produces magnetic field. So there is this dipolar magnetic field going around. And it means that from this particular magnetic moment, there will be a magnetic field component pointing this way. From this, it would be pointing up. From this, it would be pointing down. But there are not only these neighbors, there is this neighbor. And if you look at there, the magnetic field can be pointing at a different angle. And if I keep drawing, there will be a whole mess in the middle here. Because there is magnetic field coming from every single magnetic moment in this crystal lattice, and they can be interacting through the effective exchange field. So that would be a exchange interaction represented as an effective magnetic field. So for example, if our magnetic moment wants to move in a certain direction, we can say that, well, maybe there is an effective field pointing in this direction that makes this magnetic moment to move that way, or if it's precesses, there is a likely effective field that can be represented by that way. Now you need to remember that this crystal lattice is part of a big crystal. So there is big crystal, and it's not infinite crystal, which means that there is a demagnetization field inside. Demagnetizing field, or it can be expressed as a shape anisotropy. There is a crystal anisotropy, which also can be expressed with a field. So there is likely to be an easy axis, and magnetic moments would likely to be aligned along that easy axis. Or they're likely, if you look at the time dependence, and imagine they all point up, but the easy axis is pointing this way. What would happen is that they would start to move towards the easy axis. So that would be time dependence of J. It's not that the value of J would change, but rather it would be the direction. So in order to describe motion of J, or motion of this M, in presence of magnetic field, we can use this equation. But H here in this equation will be a total magnetic field produced by all atoms, and we will have to take into account the magnetic field related to anisotropy, for example, shape or crystal anisotropy, to the fact that this has a certain crystal lattice. We would also have to take into account that there might be different domains. For example, there can be part of this magnetized one way and the other part magnetized that way. And there are dipolar forces acting, dipolar magnetic fields produced by some areas of this magnet. Also, there can be actual external magnetic field that we can apply, H. Actual external magnetic field. So to summarize that, first of all, we still can track motion of single magnetic moment, but it would be more interesting to track it macroscopically. So for that, we will write, instead of dj, we will write dm dt. And dm dt, m is the magnetization of that. Now, you may notice that J is on the left and right side of there, and from J you get M by multiplying by constants, and that constants will just disappear on both sides. So you can replace J with M on both sides, and the rest stays the same. So dm dt would be equal to gamma mu naught M cross H, and that would be an effective, H effective magnetic field. Now that H effective, as we discussed, effective, this is a magnetic field that goes from applied H. I will just use H without any indexes. Then there can be exchange field produced by neighboring atoms or close by atoms. There can be anisotropy field, and that anisotropy can include all possible fields, and etc. So what I'm saying is that motion of local magnetization of certain area of our material, or all magnetization, let's say you can integrate over the whole material, is still described by the same equation that we discussed a while ago. So this is a very important equation in magnetization dynamics, and it has a name. So it's Landau-Lifshitz equation. So Landau-Lifshitz equation is an equation that describes motion. So if you solve this, the problem solving this equation is not the problem of solving it, because it's fairly simple equation, but the complexity of this equation is in this effective magnetic field, number one. And number two is that if you're looking for not magnetization of the whole sample, but magnetic moment of particular atom, then basically you have to solve this equation for each magnetic moment that builds your magnetic material. And imagine that you have two of them, 1 and 2, at arbitrary angles. If I look at this magnetic moment, it produces magnetic field somehow. So effective magnetic field probably is pointing, I apologize for the background noise you might hear. There is some construction happening. So this magnetic moment produces field pointing, for example, in this direction. So what would happen is that this magnetic, the number one will start move towards the field. Now, as you see what is happening, so magnetic moment number one, this one, is moving. What it means is that magnetic field produced by that number one, it was like this, it was pointing this way, but as it starts to move, for example, if it moved to this direction, now magnetic field is different. Now magnetic field is pointing in this direction, which means that magnetic field produced by number one affects number two, and number two will start to move. Number two will start to move this way or that way. It doesn't move, but it rotates. So as number two rotates, magnetic field affecting number one changes, and that affects how number one is moving. So this is, and these are only two magnetic moments. So what is happening is that this is a dynamic system in which magnetization orientation of one particular atom is dependent on all atoms in the system, and magnetization of any other particular atom would depend on motion of this magnetic moment. So what we can add there is that this effective field is actually time dependent, and that time dependence adds a little bit of complexity. So typically, if you have just a single magnetic moment in presence of magnetic field, typically that equation can be solved. Field is constant, there is only this external field component, and you can solve it. It's a precession. We actually derived it that way. But when you have a complex system with magnetic moments, millions, not millions, 10 to the 23 magnetic moments, which each atom represents a magnetic moment, then you have to solve this, and solving it analytically is impossible. So typically you would use computer to solve this. And you can imagine that solving huge systems, it might be not possible as well, because it would require lots of computing power to solve system where every nanometer you would have 3 atoms. And for example, real magnetic material would be, let's say, millimeter or centimeter. That would be too much. So nanomagnets can be solved, but at the same time, in real life, if you have magnetic material, you don't have to represent each atom with a magnetic moment, because remember, there is a certain sizes within which the particle becomes a single domain, and a single domain particle behaves as a, you can associate a certain magnetic moment to this single domain area, and then you can study interactions of these single domains. But there is always a certain number of accuracy in these calculations. Now let's try solving this equation. Uh, let's try solving this equation for one of the particular cases. So one of the simple cases. So let's say that our effective field is just the field that we apply. So imagine that you have magnetic moment or magnetization in presence of external field. So we say that, okay, exchange field is 0, anisotropy field is 0, and we have our field that we know, the field that we apply. Now, as you remember, if you just have a constant field, the magnetization will precess, but if it points in the direction of magnetic field, then nothing will happen. The torque will be 0. So what we will be looking at is magnetostatics. And in magnetostatics, we assume that everything stays constant. And that's the previous part. But we will add a little bit to that. So we will be looking for solutions of this equation. Let me scroll. We'll be looking for solutions of this equation in a very specific form. So we will say that, okay, our magnetization is constant. It is m naught. But it has a very, very small, I would call it perturbation, but what it means is that magnetization mainly stays aligned in this direction, m naught, and it changes only a little bit. So it can precess, it can move by only small m. So that small m would be a change of m naught vector, but it would be fairly small. And this part would describe the time dependence. Now, of course, if you want magnetic moment to move, we have to apply magnetic field. So magnetic field is would have the following form. So it would have a big constant magnetic field, but it would also have a small h, and that small h is small magnetic field that would cause this small magnetization oscillations. So we take these two and we solve the Landau-Lifshitz equation. By the way, a side remark. I will use this portion of the screen, side remark. This is a lossless equation. Lossless Landau-Lifshitz equation. Notice there is no damping, which means that if you'll get precession, the magnetic moment will precess forever around the field. But let's see. So we substitute these into this equation, into Landau-Lifshitz equation. So let's substitute that. So m naught is constant. So let me write it down. M naught is constant. H naught is constant. So what it means is that when we take d dt, dm naught dt would be 0. And only this would be time dependent. So let me write it down. So our equation, Landau-Lifshitz equation, will turn into this dm dt equal gamma mu naught m naught cross h naught. Oops. Let me move the arrow. I feel sometimes people are not right in vector science, but I feel it find it very useful to write to remind yourself that these are vectors, especially if you have cross product. Okay, plus m naught cross h small plus m small cross h naught plus m small cross h small. Okay. Now, of course, we are talking about not a single magnetic moment as I wrote here. We are talking about magnetization. So when we talk about magnetization, well, first, let's assume that we had gave it enough time to saturate along the field. So, which means that m naught is parallel to h naught. So what this would mean for this term. You can pause the video, but if they're parallel, the answer is that this term would be equal 0, right? They're parallel. Now we also say that m and h are small. So what it means by small is that m naught is not small, h naught is not small. But here both of them are small, so what it would mean is this is a second order small term. And we will neglect this term. So I would cross it out with red and say neglect. Neglect this term. Okay. Now we have to decide. So that you can see that this equation turns into there's this term that's important and this term that's important in the equation. Now what we will do is we will consider a static equilibrium. So static equilibrium. And in static equilibrium, we will say that, okay, our m naught is approximately equal ms, so it's saturated. I wouldn't draw arrows here, so let me go back with arrows. Or I can leave it, but I would say that the magnitude of this m naught is approximately saturation magnetization. At the same time, let's choose the form of this m and h, small m and h, as a function of time. So we will say that h is certain amplitude e minus I omega t, and m would be m naught e minus I omega t. So what we imply by writing it this way is that our field oscillates at certain frequency omega. So we basically shake the magnetic moment with this small field oscillating at frequency omega. And our system is a linear system. So we are looking for the solution in which our magnetization responds at the same frequency, at frequency omega. So what we do is we substitute these two into this big equation. So what we will get if we substitute minus I omega m equals 2. Now we have to find we have to set the coordinate system. So what it means is that, for example, if this is our m capital M naught, or m, then we would assume that this is our z-axis, and x and y axis are in plane. So if we introduce it this way, then you would see that there will be only the magnetization would be static in this direction. Will be almost no change in this direction. It will oscillate in xy direction. So now what it means, there would be only z-axis, z unit vector, z like k, cross minus omega. I will put two omega m's omegas here, and I will write here what that is, plus omega naught m. So I would encourage you I would encourage each of you to substitute these. And substituting this would mean that this is a vector, this is a vector, of course. If you substitute these two H and M time dependencies in this form into this equation without the first and the last terms, just these two terms, you should get something like this, where I introduced omega M equal to minus gamma mu naught ms and omega naught equal to minus gamma mu naught h naught. So this what we did, we went from the very general Landau-Lifshitz Gilbert equation, which looks like this. Let me highlight it. So we went from a very general Landau-Lifshitz. Oh, let me use much bigger highlighter. Equation that looks like this. By simplifying it very much, so we neglected exchange and resotary. We just assumed that we have this effective field in certain direction. Then we said that magnetization doesn't move much. We look at the very small oscillations. And we said that these small oscillations, we neglect high order terms. It's magnetized along the field and it's just small oscillations. And we are looking for this harmonic type of oscillations at a certain frequency. And if you substitute these, then you will get the equation. Exponential parts will cancel on both sides of the equation, and you'll have only this z unit vector across this expression here, where we introduce these two. Now, in quiz number 6, I would ask you to, it won't be quiz, it would be an assignment. I would ask you actually to substitute this into the Landau-Lifshitz equation and derive this equation. Now the next step. So this equation here, it's equivalent to torque actually. If we solve this for H or for M, we can write it down using the components. So we would say that there is X and Y components of H and M. So again, let me write. So we say that M is our MXI plus MYJ, and H would be HXI plus HYJ. J roof, I roof are the unit vectors. It's like IJK. Then this equation can be written in a different form. That can be, I'll write it in the matrix form, HX, HY equal to 1 over omega M, omega naught I omega minus I omega, omega naught. And that is times mx my. All right, now it is time for you to get ready to pause the video. So as you remember, this is our H vector. This is our H vector. You should know that from linear algebra. It is equal to, this is M vector. This thing is something that sits here. What is that thing? So this is an excellent place to pause video and answer that question. Okay. Now I unpaused it. So as you remember, we were writing something like this. H is equal to chi m. Remember that? And chi is actually our magnetic susceptibility. No, not something not right. Of course, it is not in this form, but m equal chi h. Yes, thank you for correcting me. So chi is m over h. M over h. Let me write it down better. M over h. So but at that time, we always assume that m and h are pointing in the same direction. Now, we can write the same in the vector form, and in this case, m vector is equal to h vector, but in this case, we use a matrix of chi. So chi is, it's not that our x component of m is proportional to x component of h, because when we apply h in x component, our magnetization might move in y direction. And the reason for that is this cross product right here. Let me highlight it so you'd see. So the cross product is the reason why we don't have that just a single constant. And if you look at this, this is a matrix where hx, applying hx, would affect both x and y of magnetization. So therefore, we have to write it down in the matrix form. So in this case, the chi roof, chi roof is called a tensor susceptibility. It's a tensor susceptibility, and you can write this in the component form. So I component of m is equal to h jth component of h times x ijth component of susceptibility. So we can write that, for example, mx is equal to hy I xy. Now, if you look at this matrix here, well, it's an inverse susceptibility, so you have to think about how to get it inverted. But you have always this 1, 1, xx, xy, yx, yy components. So you should know that from linear algebra. Anyway, that's a tensor susceptibility, so let's write it explicitly. We have to invert that. So tensor susceptibility has the following form. It has chi minus I kappa chi. So that is our tensor susceptibility where we introduce these chi values. Chi is equal to omega naught omega m divided by omega naught square minus omega square, and kappa is omega m divided by omega naught square minus omega square. Now you see the way how material reacts to the magnetic field. Previously we were just looking at m equal chi h, and that assumes that h is constant. Now we are dependent on frequency. So here is this frequency. Let me use highlighter. Here is frequency and here is frequency, which means that if our field is time dependent, everything depends on how fast we are changing this field. And by the way, this omega m and omega naught, we introduced them before, so you can scroll back in your video. So these are the introductions. They are dependent on the magnitude of the field that's applied, and it also depends on the magnetization of the material, how it will react to the magnetic field. Okay, so now let's look at what would happen if our frequency is actually not equal but approaches omega naught. So when our frequency approaches omega naught, you will have 0 here, right? omega equal omega naught, you have 0 here, which means that chi approaches infinity. So chi is our susceptibility, and turns out that our chi has certain frequency dependence. And as we approach omega naught, it shoots to infinity. Now, of course, there is no infinity in real life. Okay, so let's go to the next part of this video. Not next part, but the next section. So we realize that there is a very interesting dependence of magnetic moment on applied magnetic field when we consider the time dependence. So now let's move to a little bit different case. So let's have Landau-Lifshitz equation written in this form: m dm actually dt equal to gamma m cross b. So what I did is I just went back to b. Okay, let's apply. We have a material. Let's again assume that our b naught is pointing upward. But now we have magnetic material, and we have demagnetization factors Nx, Ny, Nz. So demagnetization factors means that our field, and this is the z-axis, field in x would be equal to certain component, a certain constant part of that, minus nx mx. Remember, this is demagnetizing field. And nx is demagnetization factor along the x-axis. Now same can be written for by. I means internal, and that would be external. by external, b naught, minus ny my. bz internal is equal to bz naught minus nz mz. So what we wrote down here is we just said that field inside of the material should be adjusted by the demagnetizing field, which points in the opposite direction. Now what we can do now is we can substitute these fields into that equation. So when we substitute these fields in the equation, we can do some not limited, but some math. I wonder if I need to do that, or I would leave it to you. Yes, so we would get the following. Let me write down one component, dmx dt. So we substitute x components and y components of these and corresponding components here. So it's a cross product, so you can write the cross product as you know. So A cross B, two vectors. You take a determinant I, J, K, A, X, A, Y, A, Z, B, X, B, Y, B, Z. So you take this in this following form and use that to expand this into the component form. And then x component of the left side should be equal to x component of the right side. So you substitute it, and you get that your x component gamma is there, b naught plus ny minus nz, m my And the same can be written for y d m y. Actually, I will write it down. You will be able to scroll it if you're not interested in the process of me writing this. Gamma, that would be negative sign here. Negative gamma b naught plus n x minus n z, magnetization, total magnetization value, m x. You can also write d m z dt equal and write down, but to the first order, mz would be equal to the saturation magnetization. As you remember, we have our magnet pointing in the direction, magnetization in the direction of magnetic field, and we're not interested. So there is a very, very negligibly small variation of it in the direction of z, so we can write that this is equal 0. And actually from this to the first order, we can say that our magnetization z component is equal to ms. Now, so there will be component 1 and component 2 of interest, and you may notice mx, my, mx, so they're not independent. This is a system of two differential equations, and we again are looking for the solution in this form. So m should be equal to m e I omega t minus I omega t. So this is in oscillations. And notice there is no, it's just oscillation in place. So we're looking for the oscillation of magnetic moment. So if you substitute this to these two equations, these two can be written actually also in the matrix form. This is a very, very similar to this. Where is it? To this. You may notice there is mx, hx on different sides. So you can, and this is basically this equation written in the matrix form. So the same can be done with these two equations, except that we have b naught, which is a constant field. So notice there is no oscillating portion. So if you write it in the matrix form, to solve it, we'll get determinant I omega gamma b naught plus n y minus n z m. Now there will be minus b naught plus n x minus n z m plus I omega and a whole plus. So that determinant is equal 0. We are solving system of linear equations. So from this, you can write explicitly the determinant. What you will get is the following. You will get omega naught square is equal to gamma square, and there would be a product of these two. Let me highlight those. So this is this, and green. This part is this part here. I'm not rewriting those because you have it already written. So what we did is we actually found a frequency, and that is the frequency at which our magnetic moment would oscillate. So we are not looking at the m as a function of time, but we can still find it because this is the solution, and this is how it will oscillate. But what we found is that if you take your magnetic moment m and place it in the magnetic field b naught, and that is not just m magnetic moment, but that is material. So we took the material which has certain demagnetization factors, and I, x, y, z. Then overall magnetization of this part of the material will oscillate at certain frequency. So this frequency that we found here is called uniform mode. Uniform mode. And uniform mode implies that if you take material, that all magnetic moments in this material, all of them will oscillate at the same time with the same amplitude simultaneously. And this is our condition, actually. We were looking for it in this way. So magnetization would be equal to magnetization value times, and we can write it m naught or ms something, m naught. It does matter, but we are looking at it in this form. It oscillates at certain frequency. And frequency at which it would want to oscillate, this is omega naught. So when this is equal 0, then omega at which it oscillates, let me write it to clarify it. Omega square would be equal to this, equal to that. So this is the omega. This omega would be equal, we will just name it omega naught. This is a frequency at which all magnetic moments will oscillate simultaneously in the magnet. And this is a frequency that at which all magnetic moments naturally oscillate. So as you remember, if you remember from your physics course, if you take a simple harmonic oscillator like this, or with a spring from the classical mechanics course, M, K, L, G, then there is a frequency at which this thing wants to oscillate, K or M, or it can be written down for this one. So this is a frequency of simple harmonic oscillator. So similarly, in all magnetic systems, it doesn't really matter which one you take. All magnetic systems has their resonant oscillating frequency at which all of them will oscillate at the same time. So this frequency is corresponding to uniform mode, and that uniform mode is also called ferromagnetic resonance. So ferromagnetic resonance, it's abbreviated as FMR, is a resonance frequency. It's a phenomena actually at which all magnetic moments would oscillate along the externally applied field direction. And frequency of this oscillation, of course, would depend if you go here and if you look at this yellow and green parts, it would depend on the magnetization. Here is this magnetization. And it would also depend on the applied magnetic field, B. So now if we measure, so we actually can do these type of measurements. It's a resonance. So this is frequency, and that would be, we can measure magnetization, oscillation value, or we can measure susceptibility, dynamic susceptibility as we call it. Then you will see, or you can look at the magnetization oscillation amplitude, M naught. Then you will see that it has a resonance type of behavior. Of course, if you would plot it, when we solve the Landau, let me show it again. When we solve Landau-Lifshitz equation in this form, there is no damping. It's like undamped, just regular simple harmonic oscillator. But in this case, it does not oscillate, it precesses. And for this case, there is only a single frequency, and it should look like a straight line. So it should look like just a single straight line at which it wants to oscillate. This is omega naught. Now, in real life, there is damping. And we will talk in the next lecture how we can introduce this damping and continue with this material. It's a bit too much for now, but this is something that I would want you to realize that in real materials, it's not a single line, there is damping. Therefore, if you measure magnetization oscillation amplitude as a function of frequency, then there would be a resonant type of curve. Of course, the width of this curve would depend on damping, basically on the decay of these oscillations. Now, if you take a spherical particle, as you remember, and x, m, y, and z, it is sphere. It has the same shape in all directions. So therefore, if we substitute these into the frequency, you'll see that there is this term would be 0, y equal nz. This term would be 0. And in this case, our frequency will be independent of magnetization. So for a spherical particle, resonant frequency would be equal to gamma b naught. This is a Larmor precession around the magnetic field. And stronger the field, higher the frequency, which means that if we increase external magnetic field, frequency shifts to the right. Okay, I will stop this lecture at this point, and we will continue with another lecture on magnetization dynamics, and we'll talk more about this.